Okay. So, yesterday I gave you an introduction into two of the most interesting problems of condensed matter physics, right? Metal-insulator transition and complex or glassy behavior. Is this too loud? Okay, so today I'm going to describe some of the experiments that we have done to probe this glassiness. In particular, we've done several experiments to probe the relaxations of conductivity using different experimental protocols. So this is what I'm going to describe today. So this is a review of what I talked about yesterday. Basically, the problem that we have is the problem of electrons that interact by a strong Coulomb interaction, and they also live in a random potential. The system that we study is a 2D electron system in a silicon MOSFET, where by changing the voltage on the gate, we change the carrier density. And actually, the carrier density is proportional to the gate voltage because this is just a capacitor. You have metal electrode, you have an insulator, and then another metal electrode. So when I say we change the gate voltage, I'm really saying we change the carrier density. So when we do that, so we change the gate voltage or carrier density, the conductivity changes, we have more and more carriers, conductivity goes up. Also, we studied two different sets of silicon MOSFETs that have very different amounts of desolder, and as I said yesterday, the desolder comes from the impurities that are located randomly in this oxide. And it turns out that the mobility to the electron gas has a peak. So this peak mobility, this is kind of a standard, it's a conventional peak mobility at 4.2 Kelvin is usually taken as a rough measure of disorder. So sometimes I will be saying these are the data obtained on high mobility samples. It means samples with a small amount of disorder. Likewise, low mobility samples have a lot of disorder. And I try to put all that on the slides just in case. Okay, and the goal was to probe the dynamics and see whether we can find some evidence for the metal-insulator transition in this way, because as I said yesterday, even the existence of a metal-insulator transition in 2D was controversial and unresolved, and also to see whether maybe there is also a glass transition. So here is one set of MOSFETs. These are high mobility or low disorder silicon MOSFETs, and the exact same devices were used by another group to study these samples in detail using other techniques. So this was kind of, I think, a good choice to study the dynamics because they were already well characterized by other people in other ways. So this is similar to what I showed you yesterday. On the y-axis, we have the resistivity as a function of temperature, and different curves correspond to different carrier densities. So at the lowest density, we have insulating behavior because the resistivity increases exponentially up as temperature goes down. And at higher densities, we have metallic behavior where we see a drop of resistivity this keeps sliding down as temperature goes down. And then there is this separatrix where the temperature dependence on the resistivity changes sign. So the question was whether this coincides with the metal-insulator transition. And so other people tried to determine the critical density for the transition in different ways. One was to see when this strong localization at low densities ends. So at low densities, we have a strongly localized state. We have exponential temperature dependence on the resistivity. So you can, for each curve, you can fit the data to this kind of expression, extract the activation energy, and then see how activation energy is decreased as you increase the density, as you go this way. So when the activation energy goes to zero, you can say, okay, this is where we are no longer in the insulated state, and this is where the critical density should be. So it turns out that in these samples, in these high mobility samples, this separatrix essentially coincides with the critical density for the metal-insulator transition. And also other people have used some other techniques. It turns out that in the insulating regime there are some IV non-linearities which disappear, which vanish at the same density. So this was additional evidence for for this density in the critical density for the metal-insulator transition.
Yeah, I was wondering, you would expect Efros-Kolosky, wouldn't you expect?
Yes, you
so
would. And actually, when you go deeper down to lower densities, you do see Efros-Kolosky, Grachenko did this. They get 1/2. But both they and we, when you're kind of closer to the transition, this change is not really that big.
Okay.
So you can fit it either to this, or you can fit it to. It doesn't really make a difference what quality you have here. But so whatever fit you choose, you end up basically with the same value.
So EA is the kinetic energy, is EA?
It's the activation energy. So you just fit each curve to an exponential temperature dependence, and you extract this activation energy and.
But it's completely phenomenological.
Yes, it is. But as I said, they also. I will show you later. We also made fits here, and it confirms really that this is the critical density. Also that later, but they used other methods, and they all agree in this case of high mobility samples that these parametrics more or less coincide with the critical density. Okay, so this is the method that we will use later to determine the critical density also in low mobility samples.
I also have another question about consistency of this data with or relation of this data to Capitolnik stuff, where there's an intermediate, another step. Do you understand?
Capitolnik, this was our superconductor and insulator transition.
Oh, okay, so that's
yeah. Well, these people, okay.
It's just different material. It's a superconductor material.
Yes, but they say it's an insulator, then they say, okay, it's really a metal, but now it's no longer. This is.
So this is much cleaner.
Yeah.
Cleaner in a sense.
Yes. Yeah, because there are. Well, okay. The answer is really no as I show on the next slide. Okay. It is cleaner for high mobility samples where the disorder is relatively low, and most people have worked on these samples, and we have done both. So. I'll explain later what you get in general and in these special cases a function of disorder. So I will show later that the glass transition in these samples also more or less coincides with the critical density for the metal-insulator transition. So for high mobility samples, everything more or less takes place at this density. Now, if you look at the samples with much more disorder, the situation is different. And note that now I'm plotting conductivity, so it's the inverse of what we had on the previous plot, as a function of temperature, and on top we have the high densities. So at the high densities, you cannot see it on this scale, but the conductivity very weakly goes up as temperature goes down, so it's a very weak metallic behavior. And this is consistent also with other studies for highly disordered samples. You no longer see this big increase of conductivity. This effect is very weak. But then we again see this separatrix here. And as I'll show on the next slide, the critical density we determine the same way as we did on the previous slide. Namely, we fit the data at the lowest densities to an activated temperature dependence. We extract the activation energies and determine the critical density. Actually, maybe I can show it right now. It doesn't matter. Okay, so it's just here. So it's just this data at the lowest densities. You feed them, you extract the activation energies, they go to 0. And then you get something that is very, very different from this separatrix. Okay, so this was very surprising, but this is what we obtained. And as I'll show later again, the glass transition, it will turn out to take place here at a density that is above the critical density, that is on the metallic side of the metal-insulator transition. So what does this mean? This means that here you have an intermediate phase, which is a very poor metal. KFL is smaller than 1. It's a metal in the sense that in the 0 temperature limit, conductivity is finite, but it's really not very good, and the temperature dependence is insulating light. Okay, so
how did you now did what Leo was testing before in the whatever glassy phase or insulating phase fit to Shklovsky or something? Do you get a different value for AC? Or
no, I mean, again, Shklovsky really, I mean, here you see you don't have that much of a change. It's 1.5 orders of magnitude to be able to distinguish these exponents very well. But we tried both. You can take just either simply activated, or you can fit it just as well to Shklovsky, Mott, and you end up with the same MC. This is a big difference. Okay.
If I try any scaling here, it doesn't seem like much is happening with AC. It's really just from the activation.
Yes, it's from the activation energy. So I'll show you. I mean, it will, I hope, become more clear later as I show more data. So what is the temperature dependence here? Okay, so this is some kind of phase which I'm claiming now is metallic, and we'll show later that this is glassy. So first of all, when we found this, it was strange. This is not what we expected. So we tried to feed this data to something, and this is shown here. So we tried the obvious things first, like log T, which is what you expect from weak localization. You try all kinds of things, nothing works. So phenomenologically, we ended up with something like this. Okay, it's a power law with a strange exponent 1.5. So it's a constant value, 0 temperature, plus this. Okay, so this was strange, but this is what we obtained. And in Fermi liquid, for Fermi liquids, you expect to get an exponent 2. It's supposed to be T-squared temperature dependence. So this is one signature of non-Fermi liquid behavior. And the good thing is that, one good thing is for the critical density, we get a power law, temperature dependence, which is what you expect in the vicinity of the metal-insulator transition. You need to get power laws. So this is, in general, it is okay, but it was strange. And however, at that time, there was also a theoretical work going on in parallel, also at the magnet lab at FSU, in the group of Vlado Brosavljević, where they looked at the transition from a Fermi liquid to an electron glass. And they did predict, in parallel with the experiments, but independently, the emergence of some kind of intermediate phase, and they found precisely this kind of temperature dependence with the exponent of 3 halves.
Excuse me, here's a why. So, why for the metal, the conductivity is increases when the temperature increases?
Yes.
But this is the metal.
Yes.
When the temperature increases, the conductivity also.
Well, I said, okay, this is why I started my first lecture yesterday. The definition of a metal, the distinction between metal and insulator can be seen only at 0 temperature. Mm-hmm. Right, so what is important is the value of the conductivity at 0 temperature. So as long as the 0 temperature conductivity is finite, not 0, this means that it's a metal. And most people fail to remember that similar situation is actually seen in doped semiconductors, such as phosphorus and boron-doped silicon. At high densities, you see also very weakly what you would say metallic temperature dependence. Then you see an insulating-like temperature dependence. Conductivity decreases, temperature goes down, but it goes to a finite value. But you're still in the metallic phase. And only then you undergo the metal to insulator transition. So it's really analogous to that. This is a general case.
Is there a simple argument for the 3 halves?
Excuse me?
Is there some simple argument for the 3 halves?
Not that I know of. Maybe somebody else does. But I mean, I don't know. I mean, this is I mean, you can look this up. This paper, it's short. So maybe, I don't know.
Okay, but is that something that's now conventional wisdom, or is that like A theory? Or?
I think 3 halves is seen also in other kinds of systems, and maybe, heavy fermions and in the non-Fermi liquid systems, it is seen in 3 halves. But I don't know whether, the microscopic origin would be mechanism would be exactly the same. But actually there is a review paper by Miranda Dobrosavljević on non-Fermi liquid systems, and I think they have a lot of discussion about this. So you can find, various systems where this kind of thing appears.
How did you define metallic glass?
Okay, I haven't said anything about the glass yet. I haven't showed you any evidence for the glass. Metallic, I say it's metallic because in the zero temperature limit the conductivity is finite. And it's a glass because it will, as I will show you, exhibit glassy dynamics. Just like, or almost like the insulated phase.
But when you were discussing critical density, you were talking about glass density?
What I'm saying is that in general there are two transitions taking place, the metal-insulated transition and the glass transition. Okay, and in this case, when we have lots of disorder, they are very distinct, and in high mobility samples, this intermediate phase more or less disappears and they all coincide. Okay, all right. So this was for low mobility samples, and I said that in high mobility samples, the critical density and for the metal-insulated transition, the glass transition coincide. However, in these samples, you can also see the emergence of the intermediate phase when you apply magnetic field. So this is for high mobility samples. This is the density. Now we have a magnetic field, and this is a zero temperature phase diagram. Okay, so in zero field, our critical density for the metal-insulated transition and the glass transition within the error are almost the same. I will show you later how we determine this, but the point is that as we apply the field on, we start seeing the emergence of this intermediate phase, which exhibits non-Fermi liquid temperature dependence of resistivity. So I'll show you a couple of examples. So for example here, if we fix the magnetic field and we look at the temperature dependence of conductivity, this is what we obtained. Okay, so again, we didn't know what to expect, even though we had done the other work before that. So we tried different things, and it turned out that it fits best in this way. So it's again, here it's plotted versus t to 3/2, so this is why these are straight lines. And when we got this result, we were really surprised because it's exactly the same as what we had before. I think it's just amazing that physics works. So, well, I think it is incredible that everything is so consistent. So here, these fits look nicer, I think, than those I showed you before. And you can extrapolate better to zero temperature. So you see that we obtain finite values. So when you look at zero temperature conductivity as a function of density, so you're reducing the density and you want to see how that changes.
Excuse me.
Yes. Excuse me?
So the big delta is in plane.
Oh yes, I forgot to mention that. That's important. It's in plane. And this is why these 2D systems are nice again, because if you put the field in the plane, then there are no orbital effects. The field couples only to the spin. So if you see something happen, you can say, okay, you can separate the spin and charge effects. So this is nice. So so you can forget about orbital effects, and what we see, has to do with the spin. Okay, so we look at the zero temperature conductivity, how it changes with the density. So this is shown here, and again, it's a function of reduced density. So as we approach the transition. And these data are shown for 3 different fields. You can see that in all cases we obtain a power law decrease, which is exactly what you expect in the vicinity of the quantum phase transition. And within the error, the exponent is the same. There was another earlier paper which was done in the zero magnetic field. Now, if you remember what I showed you yesterday, the resistivity on the metallic side in high mobility samples decreases and then it kind of saturates. So they looked at took the value of where it saturates and wanted to see how this changes as a function of density as you reduce the density. So they obtained some exponents like this. Now the quality of those data was not that good and so on, but I think it's a good indication, good sign that what they obtain in this way is very similar to the exponents you obtain at these lower fields in a magnetic field. Okay, so we see then again that even in these high mobility samples, in some cases you can, this intermediate phase emerges. So the phase diagram, zero temperature phase diagram that we established so far is the following. At the lowest densities we have an insulator because zero temperature conductivity is zero. At the high densities we have some kind of metallic behavior, and we haven't studied this regime in any detail. However, there are many other groups that have studied this in a lot of detail using different kinds of techniques. So what I want to do is we want to focus on the regime of densities below this separatrix. So we find that there is a range of densities above the metal-insulator transition where temperature dependence of conductivity is has this non-Fermi liquid-like behavior, and so it's you can call it, some people call it strange metal or a bad metal because KFL is less than 1. And again, I'll show later that the glass transition takes place here. Okay, so this is this intermediate glassy phase, and in high mobility samples, all of these densities merge. In other words, the intermediate phase essentially disappears in zero magnetic field.
So you're going to show us later that NG specifies the glass transition.
I promise.
But there's a region between NG and the separatrix which is behaving as a metal, as a pure metal?
Well, no, because it's still I mean, okay.
I'm confused about that region.
I know it's a small region. You cannot really fit. It's a very weak temperature dependence. It's kind of insulating like because conductivity decreases, but you cannot fit it to anything. And it's not a good metal because KFL is less than 1, so it's just kind of close to the glass transition. And
I'm wondering if there's some underlying microscopics that's going on there that I need to think more carefully about.
I wouldn't think so. I mean, it's a very small region, and in some of these low mobility samples, you don't even see this kind of metallic behavior, and this is also kind of weak. I mean, these curves are mostly flat. So, I mean, I don't think so. You will see from the data shown today, and especially tomorrow from the noise, that this is a really very sharp, well-defined transition here. So, okay, yeah. All right, so finally, so how do we probe glassy dynamics? I said at the beginning of my yesterday's lecture that there are essentially two ways. One is to prepare the sample in a glassy phase, where, for example, you cool it down rapidly, and then you apply some kind of perturbation, look at the response. Or you can study the fluctuations, and I'll talk about that tomorrow. So today we are focusing on this first method. And since we have MOSFETs, we can change the density easily, and we are also interested in the charge glassiness. The most convenient perturbation that we can apply, and maybe most relevant one, is to change the gate voltage or the carrier density. So we want to change the carrier density and see then how the conductivity relaxes towards equilibrium. In other words, how it changes with time after the perturbation is switched off. So similar procedures, protocols were used by Theo and Yahoo for work on electron glass in indium oxide. One difference between their work and ours is they're always very deep in the insulating regime, whereas we span the metal-insulator transition. We are never really deep in the insulating phase, and also in their case the perturbations are relatively small. They also make a MOSFET structure, even though this is a completely different film. You can always deposit some kind of insulator, actually grow the film on the insulator. You can put the metal on the other side, you have MOSFET structure, and they also apply the gate. But in their case, they can only accomplish very small change, maybe 1% change of density, whereas we can do much more. So that's just, okay. So the first protocol was a rapid change of density. So I will explain this carefully, I hope. So these are the data, and these two show the experimental protocol. This is what we do with gate voltage as a function of time, what we do with temperature. Okay, so what we do is we start from a high temperature. It turns out that in this case 10 Kelvin is high enough. And you need to start from high temperature because, as you will see later, at low temperatures there are all kinds of out of equilibrium, history-dependent effects taking place. You need to warm up to erase all that memory. So each time for each measurement we start from high temperature. Okay, 10 Kelvin, then you fix your gate voltage, your initial density at high temperature, and then you cool down to the measurement temperature. So after some time, After some time at the measurement temperature, you change the density quickly to another value. And when I say quickly, it's about 1 second. It's how much time it takes us to turn it off, basically. So, and the resolution, measurement resolution is, 1 second. So we are looking at much longer time scales, as you can see here. So in this case, for this particular example, the initial density was somewhat above the Ng, close maybe to that separatrix, still not very high. The final density was slightly, in this metallic glassy phase, slightly above the critical density. So what happens with the conductivity? So we start measuring the time. The relaxations, our zero time is here. After we change the density, we start measuring what happens with the conductivity. So the conductivity, since we are going to lower density, should decrease, according to what I showed on the first slide. And it should stop here at this red dashed line. So it should go down to here, maybe like this. However, you see that it overshoots this equilibrium value, and in this case by about 2 orders of magnitude. It goes away from equilibrium first, and then after some long time, it starts approaching the equilibrium. So how do we know that this is the equilibrium value for this new density? Well, you can always warm up to 10 Kelvin, and then when you cool back down, that density ends up in this place. Okay, so we know that this is the equilibrium conductivity corresponding to the new density. So this is, of course, very strange. I will talk about this later. So this is again the measurement at 1 temperature. Now what you need to do, you need to repeat this for other temperatures. Again, warm up, cool down, do all this. So
this perturbation in temperature,
this is
the second perturbation in temperature?
this is not a perturbation. Okay, this is a check.
Yeah, you change it, right?
Yeah, yeah.
And then at fixed voltage, that's setting your relaxation time equilibrium? Is that telling you?
This, okay, here, this keeps approaching something. So we want to see whether this corresponds to the equilibrium value. So we warm up to high temperature and then cool back down, and it stops, at this value. Okay, it turns out that here we do not see any relaxations following after we cool the sample down. And I will talk about that more tomorrow a little. But
you don't know that when you cool it down, then you're starting an equilibrium situation, right?
sure, but you can check. You can warm up to 100 Kelvin, you start from room temperature. You always end up with the same value. You don't see any relaxations. So, it seems to be an equilibrium value. So
when you pull it down for your check, you don't see any overshoot?
after we cool it down, we don't see any relaxations, in fact, after we cool it down.
I mean, I'm just wondering, I can't tell because,
No, even if you look carefully.
if I zoom in on it,
No, you cannot see it. You cannot see it. We are not quite sure why this is the case, but maybe because, one reason may be because this change of temperature is very much smaller compared to the Fermi energy, to the relevant energy in the system. So maybe this is a very small perturbation. And this is why I have this here to show you that this kind of perturbation, when you change the density, is a very large perturbation. So this may be one reason. And however, I will again talk about this tomorrow. After we do change the temperature, we see some change in the fluctuations, but not in relaxation. So maybe because it's a very small perturbation. So, but the average is always the same. So this is the equilibrium.
And in your protocol, did you apply a large number of final densities? I mean, in terms of, I guess I'm trying to understand that.
Okay, this is why this experiments took like, I don't know, 2 years, I don't know, we lose track of time after some point. So, yeah, I'll do that. Yes, we tried everything, all combinations of everything.
I'm just trying to...
Yeah. I hope it will be more clear as I move on and show more data, but yes, we tried everything.
Could you comment a little bit how you measure the temperature?
With a thermometer next to the sample.
So you're measuring like the temperature of a bath?
Well, the samples are actually in the vacuum, and they're mounted. The thermometer is mounted next to the sample. And these are, very high temperatures. We've done lots of measurements and all these things, and there is no problem in cooling the sample at these temperatures. I mean, you start getting into problems at maybe 200 millikelvin, 100 millikelvin and below. But this is a high temperature, 3 Kelvin, 1 Kelvin. So yeah. So I mean, as I said, these things have been studied, and we've been working on MOSFETs. But yes, you do worry about all these things, and you check everything carefully. So anyway, so this was one temperature, one set of combination of densities. For the same initial and final densities, you do the measurements at more temperatures, and here are some of them. So on this plot, we are dividing the conductivity as a function of time for each temperature with the corresponding equilibrium value for that temperature. So for each temperature, each curve, the equilibrium value is here. On this log scale, it's here at 0. So you can see at high temperature, all these curves overshoot the equilibrium. They go down away from 0, they go through minimum, then they go back up and approach the equilibrium value. As you move down in temperature, this minimum moves to longer and longer times. In other words, as temperature decreases, relaxations become slower and slower. They always look the same. Eventually, at some temperature, like here, the minimum falls out of the experimental time window. We don't want to wait anymore. So we only see this initial relaxation, and these are even lower temperatures. And so, yeah, we went down to 24 in this case. So you get a bunch of data. So what do you do with this? Now we want to, try to learn something about relaxation from this. So first we want to see how this approach to equilibrium takes place. Okay, so you notice that all these curves are similar, and for us who work with metal-insulator transition and scale the data, we have this urge always to try to collapse the data. So first we look at these times, long times, after the minimum, and we try to collapse them. So you shift them this way.
Just to be very clear, because
this
is always the same voltage.
This is always the same combination, initial and final densities. So this is the example for that.
Just different temperatures to which you put down in this system.
Yes, just different measurement temperature. But the densities is the same. Well, you can't change everything at once, and you don't know what you're doing. Even this is kind of complicated. So we looked at these long times. So this is shown here. Okay, if you rescale the time axis, you shift the curves, and you see you can collapse them. You don't see very well. It's a kind of, slot is very kind of squeezed. But they do collapse pretty well. You cannot, with the same renormalization of the time axis, collapse the relaxations at early times. So we look at this approach to equilibrium here, and it turns out that for all these temperatures, you can fit the data to an exponential dependence. So, So from that, you can determine, so for each temperature, you determine this value of tau that you use to collect the data. You find the temperature dependence of this equilibration time, and you find that the equilibration time is simply activated with some activation energy of 57 Kelvin that we do not know where it comes from. But anyway, what this means is that after a long enough time, because this is an exponential relaxation, it means that after a long enough time, the system will eventually reach equilibrium.
Excuse me. So, just for the experiment, so if you suddenly increase the temperature or increase the density curve, but still the density is smaller than ng, can you observe the signal result? Like the conductivity goes up and then.
In this case we decrease the density.
Yeah, this is
so the conductivity was supposed to become smaller, but it became even smaller. So this is why we see the minimum. If we increase the density, the conductivity is supposed to get bigger. Again, it becomes even bigger, and we see maximum in that case. So it always overshoots the equilibrium. It goes, further away from where it's supposed to.
After it reaches the maximum.
And then it goes back down and approaches the equilibrium value. Yes.
An increased temperature or?
As a density, always a density.
Okay.
Yeah.
Well, so if you increase the shift in density, but around a higher density, this affects the overshoot is a function of being close to NG.
I will show all this later. I do have, I'll show you when it goes away and so on.
But it is the property of being close to NG.
Oh, yes, yeah.
That's how you define it.
Yeah. Well, no, but okay, let me go on. Okay, so we found this from these fields, we found this kind of temperature dependence. So what does this mean? It means that the temperature, assuming this field extends all the way to zero temperature, and we do have 4 or 5 orders of magnitude, which is not too bad. This implies that in the zero temperature limits, equilibration time will diverge. In other words, the glass transition will take place at zero temperature. Okay, and recently there was some numerical work by Daniel Grankel where he found a diverging equilibration time for a 2D Coulomb glass at zero temperature. And this is significant because, as I mentioned yesterday, people have been simulating this Coulomb glass for several decades. And only very recently he obtained these results. Although the details do not quite agree with the experimental ones. In this paper, he also showed aging that I will discuss later on, but unfortunately Daniel passed away 3 years ago, and I don't know if any of his collaborators will continue this work. So, okay, so let's see. So this is the approach to equilibrium. Now we want to see how this initial relaxation takes place. So before the minimum, we want to see what happens at early times. Again, you notice the curves are similar. You try to collapse them. So it took a little bit more work, but we were able to collapse all the data for different temperatures or many orders of magnitude. It was a little bit more difficult, but basically the curve that describes all this data, the relaxation at early times, can be described as a product of a power law and a stretched exponential temperature dependence. Again, this is for the same combination of the initial, same initial and final densities as before. So we get these exponents that are very small, and they are again obtained for this particular final density. So these are these kinds of relaxations are typically found in glassy systems because they indicate there is no single relaxation time, but rather that you have a broad distribution of relaxation times. Then we also find that this time that goes into this stretched exponential also depends exponentially on temperature. Here we have, lots of orders of magnitudes with some kind of, again, activation energy of about 20 calories. So, let's see. Okay, so we obtained this for this particular final density. Now what you need to do, you need to go back and repeat everything for other final densities and try different combinations and so on to determine how these exponents, and this depends on the density. So this is a lot of work, really. So what you find is that this time that goes into stretched exponential depends on the density in this way. And this is shown here. It goes as it's an exponential function of the square root of the density. Again, this is purely all empirical, phenomenological. This is what comes out of the data. And these are the exponents that go into the stretched exponential. Beta, red points, is the exponent that goes into the stretched exponential, and alpha is the exponent of the power law component of the relaxation. Now, this is all very complicated. However, what we're really interested in is the zero temperature limit, because the equilibration time diverges at zero temperature, indicating a glass transition there. So when temperature goes to zero, you see that, what happens with this? This disappears basically, and the relaxation, becomes 1, and the relaxation becomes a pure power law. And turns out this is, again, power law is a good sign because that's what you expect when you have a phase transition at zero temperature. And also what we showed, what the previous slide really shows, the fact that we can collapse these data, we can scale them in the vicinity of zero temperature, is what you expect in the vicinity of quantum phase transition. So we have power laws and we have scaling. Yes, and what I want to mention here is also that, let's see, this exponent alpha, which is the exponent of the power law, goes to 0 at this value of density, which is the one that I called Ng before. So this is the first evidence that this is the glass transition density, and I will show more evidence tomorrow. And there are no relaxations observed in the 0 temperature limit for densities higher than this. At finite temperature, you still see some slow behavior, but it's very weak, and it's a finite temperature effect. And another thing that I'd like to point out here is this density dependence that goes as square root, because in 2D systems, we know that the ratio of the Fermi energy to Coulomb energy goes as the square root of the density. So the fact that this depends in this particular way on the density is a strong indication that these slow relaxations are dominated by Coulomb interactions. So what have we learned so far? Well, the data strongly suggests that for densities less than Ng, there is a glass transition that takes place at 0 temperature, and the evidence for that has been a diverging equilibration time, scaling of these non-exponential relaxations, and power laws that we obtain in the 0 temperature limit. I also want to remark that very similar behavior is observed in spin glasses. In spin glasses, the glass transition is finite. However, as they approach, as they lower the temperature towards this glass transition, they also see the same kind of relaxation, power law times crash exponential, which is reduced to power law at Tg. And everything is really very similar, except that in our case, Tg is 0. In our case, because temperature is a relevant variable, these exponents, alpha, beta, they depend on temperature. In our case, they depend on the density, because we see a glass transition as a function of density. Okay, so at finite temperatures, the system appears glassy for short enough times. I want to mention that these equilibration times actually at fairly high temperature, 1 Kelvin, can be very, very long. So for all practical purposes, at these temperatures, you are out of equilibrium. You can study the glassy behavior. And, okay, so Coulomb interactions seem to dominate, and I already said all this. Okay. So, again, this is interesting. We will discuss this later on. I don't know what the origin of this is. So far what we have established is, again, this phase diagram. Before I showed you the 0 temperature phase diagram. So we have an insulator, we have some strange non-Fermi liquid metal, and we here find that all this whole range of densities exhibits glassy dynamics, which so far has been manifested in this way. Okay. And these effects become observable only when the temperature is low enough, because this is a 0 temperature phase transition. So you have to be close enough to see some effects. Okay, so are there any other manifestations of glassiness? Can we also find some kind of behavior, other types of behavior that are similar to what is seen in other glassy systems? So as I just mentioned, if our measurement time is shorter than the equilibration time, then for all practical, then the system is out of equilibrium. And this is the case that we are going to study. So the equilibration time is somewhere here, and when we do the experiments, we prepare the system, we cool it down, and then we apply after some time called the waiting time, we apply some kind of perturbation, which is what we just did, and then when we measure the relaxations, that is how the conductivity depends on time. Okay, however, it turns out that one of the main characteristics of glassy systems is that this kind of relaxation here depends not only on the time t, but it also depends on this waiting time, which is sometimes called the age of the system, because the system, you let it sit in this glassy phase for a while, and it aged, and it turns out the older systems are slower, which is maybe why it is called this way. So, okay, so this is more or less all I'm going to say about aging. One reason is I do not know much more about this than that. And also, Michelle is going to give 3 lectures on aging, starting from tomorrow. So I'm sure you will learn a lot, and she will give you some references. I've listed just 2, which are really from 2 summer schools, similar to this one. So I think this is that's why they are useful. So for our purpose, what is important is that the response, the relaxation that we measure here, in a glassy system should depend on 2 times, not just on T, but also on the history of what you did prior to the measurement. So what we want to see is whether our system also exhibits some kind of history-dependent behavior. So in order to probe that, we have used a different protocol, something that was also done previously in indium oxide films. Again, we change the density. The beginning of the protocol is the same. You fix the density, cool the system down, and then you change the density quickly. But this time, you stay at this new density only during the waiting time. And then you go back to the original density. Okay, so at the end, you have the same conditions, same density, same temperature as before, and you measure the conductivity, see how it relaxes towards equilibrium value. So we know that this is equilibrium, we already measured this in the beginning. And in this case, we can change the history, we can change the waiting time, and we can change the temperature, and we can now study systematically whether relaxations depend on this history, on history. So this is again one example for, so the initial and final densities are the same. In this case, this is in the insulating regime. And the waiting time was 1,000 seconds. The density during this time is slightly above Ng, but it is still very poor metal. Even at this temperature, we see some kind of small relaxations.
So here the temperature changes slowly. So here the temperature changes slowly.
No, the temperature, no, I mean, we cool down only initially. We change the temperature to the measurement temperature. And we don't do anything to temperature yet, anymore. So we just stay at the measurement temperature. Okay, and we have to measure the conductivity for a while. It doesn't really matter how long you wait, it doesn't change. So the only thing you change the density to some value, stay there during the waiting time, and you come back to where you were.
Is there an overshoot here?
I'll show you. Okay, so, yeah.
No, I mean in that little region.
Okay. All right, so these are some data for these combination densities for different temperatures and different waiting times. So you can see you get all kinds of things. So it looks pretty messy. It's clear that the response does depend on the history, so this is a good sign, but this overshooting is a little annoying at this point.
Sorry, I don't understand the relation of this to the previous.
This is just one example for a fixed temperature. I don't know what it was.
Okay, but because the scale is different, are the plots you're showing on next transparency?
Okay, I'm sorry.
Region or in the...
Okay, this is a sigma. Sigma is a function of time, and this is the same kind of thing we did. So as before, we are dividing by the corresponding equilibrium value, because we want to see how far away from equilibrium it is. Okay.
So why on the previous transparency, why isn't there a relaxation where you're changing the voltage? Like when you step up the gate voltage.
Okay.
In that region, if you look at the conductivity, why?
Because it's tiny and you cannot see it on this logarithmic scale.
Okay. It's much different
it's tiny because this density is very large in this particular example. Okay, it cannot see it on the large scale.
In the case when you raise the voltage, you go to a metal phase?
Okay, this density is slightly above Ng, but it's still not a metal, it's still below this separatrix. So it's close to Ng, and this is why you at finite temperature still see some small relaxation. The system is relaxing on experimental time scales. But it is not really a good metal.
But if it's not a metal, then what they were asking...
I'll show you. I mean, I'll explain in 2 slides when we see the overshooting and when we don't.
Okay. You change from the metallic phase into the glass phase.
Okay, all right. We tried all kinds of combinations. And let me say that all this only depends on the final density. Okay, the relaxations depend only on the final density.
But even without going back with the voltage, you already have aging, which things already depend on 2 times individually.
can see this again.
Well, I mean, if you just went up from T0 to V1 and leave it there,
Right, yeah.
then already things should depend on 2 times certainty.
But this is what we did
Okay,
before.
I'm
Yeah,
asking,
yeah. I mean, this is what we. This was the first protocol.
This is just cutoff for us. The other protocol maybe.
Well, I don't know. You pick whatever you prefer. So we just done both, and because then. Okay, because here we have a well-defined waiting time. In the first one we don't. So we don't. So this is why we wanted to have some additional characteristic time.
So the two controls.
Exactly, yeah. Okay, so you get all kinds of things. Here, okay, we see that, yes, the relaxation does depend on how much time you spent in the during the waiting time, okay, with the new density, because if you stay there longer, the system has more time to go away from the initial state, and this is why when you come back, you're farther away from where you're supposed to be. So the system kind of remembers how much time it spent there. But you see here, we see this overshooting, and if you look at some other examples, you see that when you have this overshooting, it does not depend on the waiting time anymore. Okay, so this was... Okay, for a while we didn't know what to do with this, so we decided to see, okay, let's see under which conditions we observe overshooting and under which conditions we don't. In other words, for which values of the waiting time and temperature we see the overshooting. So this is the result. So basically, okay, for long enough waiting times temperatures, we see overshooting and no dependence on the waiting time, and the other way around here. So, and we find that this, so these are the data, and we find that this energy scale, or time scale, is really essentially determined by the equilibration time, which does not depend on the density. Yes?
So can I think of this overshooting as basically like a melting transition? Where I melt and I lose all my memory?
Well, I don't know. I don't know anything. I mean, this is too confusing, but let me just tell you what we get out of this. So basically, okay, overshooting is observed only when the system has enough time to equilibrate at the new states during the waiting time. So when the waiting time is long enough, the system at the new density has equilibrated, then we go back to the initial density. So this is the same protocol that we used initially. It's the same experiment. We start from equilibrium. So whenever we start from equilibrium, and we go back into the glassy phase, we see the overshooting. And if, on the other hand, the waiting time is short enough, so at the new density the system is still relaxing, this is when we see monotonic dependence and when we see this aging memory effect. This is because the system is still relaxing, so of course if it relaxes, if it goes farther away from the initial states, then it will, when you go back, it will depend on the waiting time. And here, because it's in equilibrium, doesn't matter if you wait any longer, it's already in equilibrium. Okay, so this is a phenomenological observation. It still doesn't tell you what the origin of the overshooting is. Again, the answer is I have no idea. I know that it's observed in a variety of systems. There are also some theoretical models that I have no idea if they can be related to these experiments, at least not in an obvious way. But there are experiments that numerical simulations that draw some out-of-equilibrium behavior where they find these kind of effects. So perhaps it is related to the fact that this is a very large perturbation. And again, we change the density, for example, in some cases up to a factor of 7, as opposed to these other experiments where the density change is very small. These large, since we are changing the density, we expect that such large perturbations should also trigger some major charge rearrangements. So it's a really big perturbation to the system. So again, I don't know. If anyone ever can figure this out, let me know. Okay. All right. So I'm going to run out of time, but maybe I can have some more because there are a lot of questions. Okay. Okay. So there is one nagging question. So far we've seen, I think, some nasty examples of some nice glassy dynamics. But people always ask the question, how can you be sure that this glassiness is really due to the 2D electrons and their interactions and not maybe to some glassy behavior of some background charges? For example, what about these charges in the oxide or in the substrate? Of course, we know from previous work for many decades that they're all practically frozen at these low temperatures. But still, it's a kind of nagging question, and people try to always address this by, maybe changing the substrates. For example, for indium oxide, they grow it on different substrates to see whether it makes a difference and so on. And here we can do even better because we have silicon MOSFETs, we have, all the semiconductor technology behind us. So what we can do with the gate voltage, we can remove all the electrons from this inversion layer, from the interface. And we repeat this waiting protocol experiment. Because if the glassiness is due to the motion of some background charges, then even if the electrons are not there at the interface, these background charges will still keep on moving. So when you introduce the electrons, measure the relaxation should depend on the waiting time, because they could keep on moving. But if the relaxation is due to the glassiness of the 2D electrons, it should not depend on the waiting time, because the electrons were not there. And what we find, so this is what we did, and what we find that indeed the relaxations do not depend on the waiting time, which provides further support to our claim that this really glassiness comes from the interactions, from the behavior of the 2D electron system itself, and not from some background charges. Okay, so what I want to do at this point is study this aging regime in more detail. Forget about this overshooting. And we want to study this aging regime and see whether we see again some similarities to other glassy systems. So for that purpose, we are going to fix our experiments. Most of the time we'll sit at 1 Kelvin, because this is where the equilibration time is astronomical. So we know we are going to be out of equilibrium at all times. And we want to see what happens as we change the density, as we go from the insulating regime through the metal-insulator transition. So here is one example so this is again this waiting time protocol. You change the density to some value, you come back. So in this case, the initial or final density is in the insulating regime. As I said, everything depends only on this initial or final density. It doesn't matter where you go in between. And the relaxations are obtained for different waiting times. Okay, so you have a lot of similar curves. What do? And you're all supposed to rescale them. Okay, so you try to collapse the data. So we divide by this waiting time, which is the only kind of characteristic time that we have here. And so this is what people do. We find that these relaxations collapse indeed on the same curve. And what this means is that this aging function depends only on the ratio of the time and the waiting time. So it has this particular form which people call full and simple, or simple aging. We also see that we can fit this aging function to a power law for times up to the waiting time, and then the relaxation becomes slower. So this means that there is a memory of the waiting time imprinted on each of these curves. This is exactly when each one stops being a power law. Okay, so we've established that for densities in the insulating regime, we find that the aging function has this kind of form. Then we try to do this collapse for higher densities, and we find that as we increase the density, we see increasingly strong departures from this full aging. So here is one example. This is the density slightly above the critical density, and you see that you can no longer collapse them nicely simply by dividing by this waiting time. Now, in some systems, such as spin glasses, people have had problems finding this full aging for many years, and they try to see if the data can be collapsed in some other way. For example, by raising the waiting time to some exponent mu. This kind of scaling probably does not have a clear physical meaning. However, we have decided to try this, and we found, for example, that here the data can be approximately collapsed with some exponent 1.3. We decided to use this simply as a measure of the departure from full aging. So we want to see, we use this exponent Q to tell us how far away we go from this full aging. So again, you see these are the densities, critical density, glass transition. This corresponds to full aging. Then there is a very strong departure. And then it seems as if the maximum is actually the glass transition density. As I said before, it seems that there are at finite temperatures, there are still some small relaxations, but I think this is just an artifact of finite temperatures. Because these relaxations are small, we are trying to collapse small signals with big noise, and we know that in zero temperature limits they go away anyway. So the point is that there is a difference between, we first of all see an abrupt change in the aging properties and the critical density for the metal-insulator transition. So this means that there is really indeed something going on in this system. It is density, and also what this shows us is that the insulating glassy phase and this metallic glassy phase are different because the aging function is different. And this is, in principle, it should be useful to the theorists because it restricts the kinds of models that you can use to describe these glassy phases. For example, there are different mean field models of glasses. There are those that show full aging that will be appropriate for the insulated regime, and those where no such scaling is expected, but rather the aging functions have a different form. Okay, and there is only, right, okay, so here we just show that this exponent mu does not depend on temperature. This is for two different samples. Maybe there is not much new information here. There is one more thing I wanted to mention. I don't know, this may be a little difficult to follow, maybe not. So again, this is the waiting time protocol. The waiting time is fixed. We always go to the same density during the waiting time. We only change the initial density. Okay. So let's see, if we start from a high initial density and we go to some, final density during the waiting time, not final. Then we measure some kind of relaxation. Then we reduce the initial density to a smaller value and see that these relaxations become bigger and bigger. And in fact, however, if you look carefully, they have non-monotonic dependence. They become bigger, but then as you reduce the density further, they become smaller. Now, each of these curves can be fitted with this kind of function. It's a power law. This is a log-log scale. It has a power law with some initial value, or which we call amplitude. And if you look at these curves carefully, you can see that both these amplitudes and these slopes change non-monotonically depending on the value of the density. And here is the example, what we get for this amplitude, these initial values, as a function of the density for several fixed waiting times. Okay, so what you do here, we are reducing the density. In other words, the step that we are making, the change in the density keeps getting bigger and bigger, so this initial amplitude grows. So you can say, okay, you're making a bigger change in the density, this is why you're going farther away, this is why the relaxation is bigger. But then as you keep reducing the density, you're making an even bigger change, so you expect this to keep growing. On the other hand, you see that a decrease in these relaxation amplitudes. And it turns out that this happens, this peaks, just slightly below the critical density for the metal-insulator transition. And, okay, we don't have a detailed understanding of this, but I think it is plausible because it makes sense because as you enter the insulating phase, these charge rearrangements which are responsible for these relaxations, they become suppressed. It becomes more difficult for charges to rearrange because the electrons become localized. They enter the insulating regime. So it is kind of plausible, but this is just, okay, I wanted to show this, just to show you that this indicates that there is something else also in the aging properties that changes in the receipt of the metal-insulator transition, so which is distinct from the glass transition. So to summarize and finish, okay, we have found from this data so far the emergence of an intermediate non-Fermi liquid metallic phase between the metal and the insulator in general. And we found evidence for the glassy behavior for densities below this Ng. And this glassy ordering appears to be a precursor to the metal-insulator transition, at least for 2D electron system in silicon. We haven't studied other materials yet, and we found different characteristics of glassy systems, such as aging, which shows abrupt changes at the metal-insulator transition itself. So this system exhibits similarities to other glassy systems, such as skin glasses. And the advantage of using this system is that it is very simple, as I emphasized yesterday, even though this behavior is complicated, but it's simple in the sense that you have only phone interaction disorder, unlike all these other strongly correlated systems where you have other degrees of freedom. So tomorrow, this is a summary of today's talk, and tomorrow we look at the fluctuations, and I hope also to cover some work on the Coulomb rate as well. So thank you.
More questions? Come on.
So now, say you consider the 2D electron gas. What about if you consider the 2D whole gas?
Sure. I mean, I'll mention that tomorrow. Nobody has looked at the relaxations. There was some noise work, but I mean, people don't want to do these things. I mean, really, because the experiments take forever, the analysis takes forever. So sometimes I wonder why I'm doing it. Really. So it hasn't been done, but this is something that we want to do because I want to see, it's important to determine whether this is something specific to silicon or to other systems, although I think we do have good evidence that it is not material specific.
It seems for the electric gas and for the whole gas, the band structure is different. But for this situation, there's no band structure.
Yeah, I mean, as I said yesterday, everything is glassy. I mean, you'll see in cuprates, the charge carriers are holes, and everything is different, complicated, but you still see a glassy freezing of charges. So, I don't think it makes any difference. There shouldn't be.
This is at low doping?
Excuse me?
In cuprate, you see that at low doping?
Yeah, this is low doping, but now we are moving to high doping.
I was going to say,
but things are still glassy.
As a comment, you said, as a comment, you say sometimes you want to do, why are you doing it? It's beautiful data. It's really
yeah, I know. Thank you. Yeah, you can say that too, but it's tedious work, and I've had really the fortune of. I've been fortunate to work with some very patient, careful people. Who, I wasn't turning these knobs. It was my postdocs and my students, so they really deserve all the credit. And their names are mentioned on the references. For starting with Bogdanovic, Jan Jadroshinsky has been working with me for years, and another great student, Rejcevic, who just graduated actually. Her work was on cuprates.
Any other questions? Now, before Jordan makes his announcement, then let's thank the Lord.